All right, so we used hybridization as a way to explain the structure and the bonding of molecules, and it was just basically based on one atom and its directly surrounding atoms, right? But in real life, the molecule is one big thing, and so all of these orbitals are interacting with one another, and so the kind of closest to what the real life answer is actually what's known as molecular orbital theory. And it's very similar to hybridization, but instead of just considering bonds between, one atom and its surrounding atoms, we're considering the whole molecule, right? So similar to hybridization, but it's for the whole molecule. And so similar thing here, right? If we have a 1s orbital and then another 1s orbital, there's two ways that these waves can interfere, either constructively, and so they'll sum together, and this will actually be a lowering in energy, or deconstructively, right? If they're out of phase, then you'll get a higher energy state orbital. And so the electrons will first fill the lower energy orbital. And so this one right here would be a sigma bond because it's direct overlap. And this is what's known as a bonding orbital. And then up top here, we've got what's called a sigma star orbital. And the star means that it's an anti-bonding orbital. Right, you can see how in the bonding orbital, we've got some overlap here. And in the anti-bonding orbital, we've got opposite colors or things out of phase with one another. And so because they come from the s orbitals, they are sigma bonds. And then we can think of the same thing for p orbitals. So we have our atom and its p orbital. Right, and then these can hybridize or mix into a molecular orbital, right? An orbital belonging to the entire molecule. And then on the bottom, we'll have a pi bond or a pi bonding orbital, and they'll mix constructively, right? So they're in the same phase, right? And then in the top here, we'll have a pi star and anti-bonding orbital, anti-bonding orbital. Here, we're out of phase, and so they don't mix. Right, and so there's not really too much you have to know. Just understand when you see these diagrams what the sigma, what the pi means, and what the star or not star means, right? Bonding or anti-bonding orbitals. So let's take a look at an example of one of these. We'll never construct any of these diagrams or anything too complicated. Nowadays, it's pretty much we just do these on computers. So here, it's showing the bonding between fluorine. So this is a molecule of F2. Right, and if you drew the Lewis structure of fluorine, you would predict that it was a single bond. And so it has a bonding order of 1. Right, single bond means the bonding order here is equal to 1. And so the bonding order is also equal to the electrons in bonding orbitals minus the anti-bonding electrons divided by 2. And so if we count out these molecules here, or these electrons in these orbitals, right, we see down here we don't have a star here. So these two are bonding orbitals. So we've got 2 here. We've got a star here. That means that it's anti-bonding. Here, again, no star, so bonding. No star, so bonding. And then here we've got a star, so they are anti-bonding. And so if we count the electrons in the bonding orbitals, we've got 2 down here, and then another 6 up here for a total of 8. And then in the anti-bonding orbitals, we've got 2, and then 4 up here for a total of 6. Do the math here, and you get 1, right? So you can see that the molecular orbital theory predicts the same thing that our Lewis structure predicts, a single bond between these two fluorines. In this case, they agree. Sometimes they don't agree, and when they don't agree, almost every time molecular orbital theory is going to be correct, and the Lewis structure is basically just an oversimplification of what's going on. And then in these diagrams here, you can see what the orbitals actually look like. And so here's the bonding orbital. You see they're in phase. This anti-bonding orbital, they're out of phase, right? Bonding orbital in phase, bonding orbital in phase, bonding orbital in phase, right? Anti-bonding orbital, out of phase. Anti-bonding orbital, out of phase. Anti-bonding orbital, out of phase. So just be able to calculate the bond order given a molecular orbital diagram and understand the very basics of it.